Hi everyone, this is going to go through what is a transmission diffraction grating and how it relates to our double slit, or how it follows on from our double slit work, and also having a look at the equation and how it relates to a transmission diffraction grating and what the interference pattern, the similarities and differences between the interference patterns. So this particular video is going to go through so the first point there, and also the derivation, and have a look at the intensity distribution of transmission diffraction grating and how it compares to that of a double slit. Okay, so what is a diffraction grating? Essentially, it looks like a little slide, and if you look at it under the light, it looks like it's almost mirrored, kind of like a CD. So if you think about it and you look at this this diagram down here, the surface of the transmission diffraction grating, or the slide, is essentially covered in tiny, tiny little scratches, and where the surface has been scratched, so you can see in these areas here, they produce like a white kind of a white line that's not transparent, and in between the scratches, or the opaque lines, there's clear glass, and essentially the clear parts are what acts like small slits or transparent slits. So it's a slide of really large number of narrow slits, and they're all parallel. It's very important, sorry. They're all lined up next to each other, and it's called a transmission diffraction grating. So the notation, we're still looking at D for the distance between the slits. Now obviously for a transmission diffraction grating, we've got lots and lots and lots of them, as opposed to just two like we've been looking at previously. Alright, so if we zoom in, and we see here that the distance between the slits is still D, and each slit effectively becomes like its own point source. So just like we saw in the Young's double slit setup, the single slit was producing in-phase light that would hit the double slits, and the double slits would work like their own point sources. The same thing happens in a transmission diffraction grating, but instead of two, we've got a really large number of point sources that are all producing coherent in-phase light. Okay, so just like when we were looking at Young's double slit setup, there's a couple of assumptions that need to be made here. And the first one is that there is a large distance to the screen, or a really big L value compared to the value of D. So L is always much larger than the value of D. And so because of that, we can assume that the light rays are going to be parallel. So once they've come through the transmission diffraction grating, they're going to be parallel to each other, and that light from each of these slits is going to hit the screen at exactly the same time. So that way the waves reinforce to produce a bright image when the path difference is 0. So that central maxima is going to be, they've all hit the screen at the same time, and there's 0 path difference. Okay, so the pattern produced in a transmission diffraction grating interference pattern is similar to that of a double slit, with a few really important differences. So if we've got a screen set up, instead of seeing bright fringe, dark fringe, bright fringe, dark fringe, all with equal spacings, what we'll see for a transmission, like a diffraction grating, is there'll be a big central maximum that will be much brighter than the others, and then as we go out from that, there'll be one that's a little bit less bright. So if we look at the graph here, we've got an intensity axis up on the Y, and along the X we've got the distance between adjacent maxima. So there's a big maxima in the middle, there's a small distance until the next maxima, a larger distance to the next maxima, and so on and so forth. And basically the intensity of the maxima decreases the further you go out from the center. So the center one is the brightest, and it'll be decreasing in intensity the further we go from that central maximum. Okay, so the diffraction grating derivation, or how we apply a similar formula, so D sine theta is equal to m lambda for a diffraction grating. The first difference is we need to get a value of D, or the distance between the the scratches on the diffraction grating. So the formula that we use for that is D is equal to 1 divided by N, where N is the slits per meter. Now, on a standard diffraction grating, it'll have the n value written on the actual slide, and then you can pop that into the formula D is equal to 1 over n to figure out how many slits per meter there are. Now, if we consider parallel rays being brought to a focus point P, we can use similar geometry to what we used for the Young's double slit derivation. Okay, so this diagram has been taken out of the core knowledge book because I thought it was quite nice at explaining what's happening for a transmission diffraction grating. So as you can see, it's very similar to the diagram we had a look at for our Young's double slit experiment, and most of the issue we have with this derivation is similar to that, in that we have to actually understand the experiment that we're looking at. So as I said before, we can consider a transmission diffraction grating. So here, instead of just having S1 and S2, we've now got S3, S4, and so on and so forth. We still have a value of L, which is our screen distance, and as it says there in the note, L must be much greater than D so that the rays will be parallel. So if we consider we're at point P, there happens to be the mth maximum along from the center, and we can consider that all of the rays that are coming to point P are going to be parallel. So you can see that from the donation, so the notation here. So they're all parallel. Now, once if we're trying to look for our sine theta, we know based on our other diagram that this here is going to be, if we had a center line going along here, that we would have this triangle here would be the same as the little triangles that we can see there, and the angle of theta would be the same. So I'll just rub that one out so we can see what we're looking at here. So we can see, because of the lines being parallel, that we're trying to work out this triangle values here. Now, sine of theta is opposite over hypotenuse. Yep, so the opposite of this side is going to be the distance between, we're actually working out this triangle up here. So the opposite is going to be the distance between S2 to R, and the hypotenuse in this case is going to be the value of D, so the distance between the slit. Now, what we also know is that point R to point P is exactly the same as from S1 to point P. So it's the same. What we're looking at is from S2 to R is actually the path difference of those two rays of light, or waves of light, coming from the two slits. So essentially, where we've got here, the hypotenuse being D, it's actually the path difference of m multiplied by the wavelength. So if we have a look at our formula, if we rearrange it, we've now got sine of theta is equal to our m wavelength over D, and we can rearrange that and move the D over to this side. So we've got our formula for D sine theta is equal to m lambda that also works for our diffraction grating. Now, one of the really important points to note here is down the bottom here, is that you cannot use the two-slit pattern equation, or delta y of lambda times by the length of the distance to the screen divided by the distance between the slits for fringe separation for a diffraction grating. And the reason for that is, unlike a Young's double slit setup where the interference pattern is going to have exactly the same fringe separation all the way through the pattern, in a transmission or a diffraction grating example, the fringe separation increases the further away you go from that center maximum. So it's really important that we don't use this formula, and that we only use the one that we've derived. So D sine theta is equal to m times lambda.